Hello, class. So on this video, we'll continue on section 2.6 in the book. If you remember, we're talking about exact differential equations. I haven't defined, well, I think I actually defined at the end of the video what an exact differential equation is. I'll review it real quick right now. Before I do that, let me note that we are skipping, well, kind of skipping section 2.5. So 2.5 is about logistic growth, but basically what's covered in section 2.5 is what I'm asking you to do in the last problem in the homework that I assigned on Friday. So that it's really not that hard. It's just a little bit of reading as you do the problem, but in terms of the actual work, it's not that bad. So that's why I thought it's good. It would be good for us to save time and for you to practice some of the techniques we've done in class for you to solve it on the homework. Okay, so in terms of lectures, we are not covering section 2.5, but again, you're doing whatever work was there in the homework. Okay, so going back to this section, section 2.6. So we saw in the previous section that we can solve a differential equation of this form, right? So this is the differential equation we're trying to find the general solution for. We can do that, and one way of doing it was if we can find an expression or an equation where we have a function of two variables equal to some constant, such that the derivative with respect to x, right? So that's why we had to go over this whole chain rule discussion. So if we take the derivative with respect to x on both sides, parentheses here. So what do we get? Well, the left-hand side, by the chain rule, we got that this was partial f partial x plus partial f partial y times dy dx equals 0. So what we saw is if we can find such function, f of x, y, and then just set it equal to a constant, and I mentioned that in Calc 3, you'll see that that is what we call a level surface. But if we can find such function equal to a constant, such that when we take its derivative with respect to x, we get the differential equation back, and in this case, partial f partial x was the 2x plus 3, and partial f partial y was 2y minus 2. If that was the case, the same y that we see in this expression is precisely the same function that satisfies this differential equation. Right? So instead of finding solutions to this differential equation, what we could do is instead just find what this function is, and whatever y we have there, well, those are the y's that satisfy this differential equation. So that was the process. Okay. Now, if it's possible for us to find such function, right, then we say that the differential equation is exact. Okay, and that's how we defined it. So that's what it means for differential equation to be exact. I don't know if I actually have a definition here in my notes, but think of it that way. Okay, that's what it means to be exact. If there is a function such that when we take the derivative, set it equal to a constant, take the derivative with respect to x, we get the original differential equation back. Now, in the case of this example, we already know there exists such function, right? Because I gave you what that function was when we were going through all this discussion. Right? The function was x squared plus 3x plus y squared minus 2y. Now we know that the function is given there. So let's say that we don't know that the function is given, and instead we want to find the function. Okay. So how do we do that? Okay, so let's go here. I'm going to add a new page. So again, we know that our differential equation has the form partial f partial x plus partial f partial y times dy dx equals 0. And like I said, in the previous example, I actually gave you what f of xy was. Right? I gave you f of xy equals x squared plus 3x plus y squared minus 2y. So let's say I didn't give you what the function is, and let's say we actually want to find it ourselves. Okay. So how do we do that? Okay, let me just write the last thing that we need here. I'm going to need this 2x plus 3. 2y minus 2. So that was the differential equation. Okay, so how do we find such functions such that when we take the derivative with respect to x, then these things match? What things? Well, partial f partial x is equal to this, and partial f partial y is equal to the other part, 2y minus 2. Well, the process is basically pretty simple. We want partial f, we want to find a function such that partial f partial x equals 2x plus 3. Okay, that means that we have, as of now, we don't know what f is, but we know that this has to be true. Well, you already know how we get from a function to its partial derivative, right? You took the derivative with respect to x. So let's undo it. Let's integrate with respect to x. Okay. So if we integrate here both sides with respect to x, what do we get? Okay. So let me just write the integral here with respect to x. And then what is this equal to? It's x squared plus 3x. Now, our function f of x, y, it's not necessarily equal to this. Even though we know that we took the partial derivative with respect to x, it's because we integrate with respect to x, it's not true necessarily that this is the function. Why? Because we know that when we take a partial derivative, anything that just contains any part of that function that just contains y's or constants goes to 0. What does that mean? Well, first of all, we should have a plus c here, right? There should be a plus c when I integrate. So I forgot to write that. But not only that, this isn't necessarily just a constant. Again, since we took the partial derivative with respect to x of a function of two variables, x and y, it could be that this c here also contains variables y. Again, because when we take the partial with respect to x, all those expressions involving just y's go to 0. So how do we account for that? Well, we need to account for the fact that those y's could still be there in the original function. So what we're going to write is plus some expression involving y's and constants. So we're just going to write that as h of y. So I mentioned before that anytime I write a function of a variable, you can think of that as just some expression involving the variable and constants. So for sure, we know that this is f of x, y. This is for sure. Now, how do we actually find what this h of y is, right? We don't know what that expression involving y was. So as of now, we don't know what f of x, y is explicitly. Well, how do we find that? Well, we use the other piece of information. We know that the partial derivative of f with respect to y should be equal to 2y minus 2. So let's write that equality. Right? So let me use a different color. Partial derivative of f with respect to y. Well, we have what our f is partial derivative of x squared plus 3x plus h of y. With respect to y, sorry. And by assumption, we know that this should be equal to the 2y minus 2. Okay. So let's go ahead and simplify this. So what's this part? Take the partial of this with respect to y. X squared goes to 0 because there's no y's. 3x goes to 0 because there's no y's. What's the partial derivative of h of y with respect to y? Well, we don't know what h of y is, but we know that it only has the variable y and constants. So when we take the partial derivative with respect to y, it's really just like taking the derivative with respect to y. In fact, it is exactly the derivative, again, because there's no variable x. So what's the partial derivative of an expression only involving y's and constants? What's the partial derivative of that with respect to y? Well, it's just a regular derivative. It's just h prime of y. And again, we know that this should be equal to 2y minus 2. Okay, the partial derivative of f with respect to y, which is h prime of y, should be equal to 2y minus 2. Okay. Finally, what do we need to do now? Remember, our goal was to find what h is. Well, here we don't have what h is, but we know what its derivative with respect to y is. So let's just integrate both sides with respect to y. And again, this is easy to integrate. This is y squared minus 2y plus a constant, some constant. So now we're basically done. We can just plug in h of y into the expression we had for our function f of x, y. So doing that, so we have x squared, oops, x squared plus 3x plus h of y. H of y we found to be y squared minus 2y. Now, what you can see here is that there are infinitely many such functions. Now, in terms of the constant, then, we could write a plus c here, right? That's certainly fine. Or you could just leave it out. The reason why you can leave it out is because, again, even though there are infinitely many such functions that satisfy this expression, we're only really interested in one of them. Right? We're only trying to find one such function, such that, you know, when we take the derivative of it with respect to x, we got the original differential equation. So you can either do two things. You can either drop the constant or leave it like that. The only thing is that you have to remember that by assumption, we want to set this equal to a constant. We want f of xy to be equal to a constant such that when we take the derivative, we actually get this differential equation, you know, with equal to 0 on the other side. Okay? So this is not the solution, right? If I ask you to solve this differential equation, this is not the solution yet. What is the solution? Well, it's x squared. Actually, let me do it like this. It's f of xy equal to c, which you can just write that as x squared plus 3x plus y squared minus 2y equals c. If you keep the constant, which again, the fact that we have this constant here kind of takes care of that, but if you want to keep this constant in the top, you can keep it and then you subtract it to the other side of the equation once you write it like this. So what I mean by that is you could also write x squared plus 3x plus y squared minus 2y plus c equals some constant d. Subtract c from both sides. These are arbitrary constants. So when you subtract d, when you do calculation of d minus c, that's just an arbitrary constant. You can just call it c again. So really, you don't lose anything in dropping it here, right? And just dropping it when you find f of xy, you're not losing anything because you gain it back by the fact that we're setting it equal to c here. And this is your solution. Now, why is this your solution? Well, it's not that this expression is your solution per se, but as we mentioned before, and let me write a star here, any y that satisfies this algebraic equation that satisfies star also satisfies, let me write it like this, is also a solution to the original differential equation, right? That's the work that we did in the previous video and what I explained at the start of this video. So we ended up from trying to find y in an equation involving derivatives to trying to find y in just an algebraic expression. And any y that satisfies this algebraic expression by the work that we showed in the previous video also satisfies this original differential equation. Okay. Now, if you notice, we usually don't leave expressions in this form, right? Whenever we're trying to find the general solution for a differential equation, usually we write y equals some function of x and constants. Now that is something I want to point out because there is a key difference here. We could leave our solution like this without solving for y as a function of x, or we could actually try and solve for y as a function of x. The problem is it's not always possible to do that. It's not always possible, given an algebraic expression, to solve for y as a function of x. And you know this, right? You've seen this in algebra. Sometimes the expressions are so complicated that you can't, right? You really can't solve for y as a function of x. So if you have, so let me write a definition here that you're going to need for the homework. This is just a quick definition. So if you have a solution, so let me write definition 1. If you have a solution to a differential equation of the form y equals f of x, so you're able to solve for y, have it by itself on one side, and have everything involving the independent variable and constants on the other side, then such solution is said to be an explicit form, or it is said to be an explicit solution. If instead we leave our solution in this form, so f of xy equals a constant, remember that's what this form is. So if instead we leave our solution in this form here, so let me write that in another color. So, or let me just write like this: a solution, or using the same notation, the same words, I guess, if you have a solution, again, of the DE, of the differential equation, if you have a solution of the DE of the form not actually solving for y as a function of x, but instead leaving it as some expression, right? So something of the form f of xy equals a constant, right? Which is what we had in this case, right? Where we, instead of solving for y, we would say, okay, any y that satisfies this algebraic expression is also a solution to a differential equation. So if we leave it like that, instead of explicitly solving for y as a function of x, then such a solution is called an implicit solution. And again, the difference is in the explicit solution, you are able to solve for y as a function of x. In the implicit solution, you don't solve for y as a function of x. So the only thing you can say is, well, I don't know what y is exactly, but I know that if y satisfies this expression, it also satisfies, or is also a solution for the differential equation. And again, the important thing about implicit versus explicit is that it is not always the case that you can solve for y as a function of x once you're in this step here. And you're going to see that in the homework. One of the homework problems, I asked you to find the general solution for a differential equation, and then I tell you to simplify as much as you can, because it's going to come a point where, okay, I can't actually solve for y as a function of x. Once you reach that point, I want you to stop and say, okay, this is as far as I can go. I tried a bunch of things. I can't write the solution explicitly, so I'm just going to say, okay, this is the solution, but it's an implicit solution. It's still the general solution because any y that satisfies this expression is also a solution. I just cannot solve for y explicitly as a function of x. Okay. Okay, so to summarize, we found a way, given that we know that our differential equation is the derivative of some function of two variables. When we set it equal to some constant, we went over the process of how do you find such function, right? You use the fact that you have these equalities, right? The fact that partial f partial x, you know it's equal to this part, so you can just integrate with respect to x, and you get your original function up to some function of expression involving y's and constants. Again, because when you take the partial with respect to x, all expressions only involving y's go to 0. So we lose that information when we take the partial derivative with respect to x. Once you have this expression for f of xy, then you use the other part. You know that its partial derivative with respect to y should be equal to this part of the differential equation. And you can use that to solve for h of y. Once you have that, you already know what f of xy is. That's not your solution. You have to set it equal to a constant so that when we take derivatives of both sides, we actually get the right equation when we have it equal to 0 in the differential equation. Okay. So we're going to do one more example of that process, and we're going to answer one important question. Specifically, when do we know that a differential equation is exact? So given a differential equation of this form, how do we know that there exists such a function whose derivative, when we set it equal to a constant, gives you this differential equation? It's not always the case. Most of the times it's not the case. So I'm going to give you a way of determining when that is the case. When are you sure that such a function exists?